with like graphing calculator on the screen.
Yeah. Well, why didn't it graph?
I only did it in 6 hours, dude.
6 hours? You could have a whole graphing library in 6 hours. There's probably actually a library out there for plots.
Well, I did most of.
Dude.
I did most of it in the library until I wanted to add the over operations and then time to do it myself.
Well, then you said you couldn't figure out how to do JSON in C#, where I mean, I'm pretty sure, like, I haven't looked at it, but I think JSON is built into C#. It's like
I
just,
thought it was too.
there's just a library that just says, create
Oh.
JSON object, pass string, now start asking for objects.
It's definitely possible that the JSON string that I had just wasn't in JSON.
Oh,
I don't know.
it's garbage in, garbage out situation.
Yeah.
Was it a corrupted JSON file? Is that what you're saying?
All right. So,
Well, as long as you had something, that was good.
this class is 300. Did we had homework, right?
Then we had a lab and then the hackathon.
All right. What was the lab? Oh, yeah. Insertion sort by, oh, that's a good one. But we could switch it to merge sort. Well, not for us to solve it, I guess. Or I'll do the easy part of merge sort, then give you the rest.
He started it. I made the joke 2 semesters ago, and he just keeps on beating the dead horse.
I just don't get why people wouldn't love merge sort.
I still think Insertion Sort is intellectual.
All right, so let's, am I sharing my screen?
Yes.
Okay, thank you. I think so. Yep. Nailed it. All right, so let's see. So last time we introduced our JSON parser thingy, right? And then we created a bunch of cards. Oh, so for the lab, you were just supposed to get minion types, right?
Yeah.
Okay.
And you said put them into an array list, and C++ doesn't have array lists. They have something called vectors.
Oh, that's right.
We weren't, like, I wasn't sure if you wanted.
I should have made it. I think I meant LinkedList, but that's fine. Whatever.
Oh.
Whatever you did. It doesn't matter. Whatever you did, it's fine. Yeah, array lists are a Java thing, right? Let's see. So I want to let's parse JSON just quickly here. I'm going to steal this URL because we want to go and look at what we need to look at for determining whether something's a minion. Was it called like type? Type. It's called type, and we're looking for type with minion in all caps. All right, so let's start off by making sure we're only building cards out of our minion types here, because right now I think our code builds cards out of everything, right? We get a card for everything. So let me do I have a compile thing here already for this? All right, so there's all of our stuff currently. Now we want to just get our ones where type is equal to minion. So let's start with that. So we're asking if curval is an object, then we can say and curValue dot value for type. Then we could do an NA for the default. we want to know if that guy is equivalent to, so that's going to come out as a string, right? We want to know if this guy is equivalent to minion. So actually, I'm going to actually not do it inside of the if here. So I think we saw that you need the type. So you need string type is equal to this guy. Then we're going to ask the question if type, is there like an equals, or do we have to, or is it defined for equal? Then we'll do all that stuff. So if I'm looking at a type that is minion, go ahead and grab the pieces of this guy, build a card out of it. Okay. Well, actually, you could have just done it with arrays too, right? But our array currently, yeah, we don't want to do it with arrays. We want to do it with something cool. All right, so
What are you gonna do with them?
sure. And then merge sort. Homework. Yeah. All right, so let's go ahead and run this. So now we should just have minions, right? I think those are all our minions. They look like minions. Yep. All right, so we have our
One
plant. Nailed it. All right. What are we talking about?
Nailed it? The Netflix show where they try to make like really fancy cakes and like stuff like that, but they like fail at it.
Oh, so the show's called Nailed It, but it's like a baking show?
Yeah, it's really fun.
Yeah, see, that seems like the type of like bait and switch thing that shouldn't be allowed. Like a show called Nailed It kind of sounds like it might be intriguing, and then you find out it's a baking show.
Yeah, you don't want to be tricked.
What if it was like a barbecue smoking show?
Oh, really?
That would be better. Oh man, I love that stuff.
Have you seen MasterChef?
Yeah, I like Gordon Ramsay. He's so mean though, but I bet you, I think in real life he's actually like a super nice guy.
Oh, yeah. And he has kids, so.
That doesn't mean anything.
Being with having kids means-
What do you mean have kids? Because he has kids, that means he's a super nice guy?
Probably. Yeah, totally.
You know, twice a week the kids are in the ER with spatula bruises.
Like, your game is all wrong.
All right, so we're gonna go ahead and we're gonna make our linked, have we already written a linked list for cards? No, we have a linked list for nodes. And what kind of thing does our nodes hold? Integers. Well, that's not any fun. All right, so let's dump linked list and make a new linked list. Okay. We'll dump, oh, hold on. So let's delete. We need URL. We don't need stack anymore, right? Although we could use, we're probably going to make a stack of cards. I'll do it like this.
I think that's what they do right now anyway, but-
Okay, dead. It's dead to us. Okay.
I probably know how to do it.
Oh man, dead. It's just dead. Here's our JSON example. We need that JSON HPP. Just cleaning up the shop a little bit. We need the URL stuff, but we don't need the GCH thing. All right, so we're gonna go and create a linked list of our cards, and then we'll write a merge sort to sort them. Okay, perfect. Perfect. And we'll see how far we get, and then we'll give Jason the rest of it, and everybody else will get like a fun assignment.
I'm not doing well for the next 2 days.
All right. So we're going to create a linked list to hold our minion cards. And the reason we're doing it this way is, as we have it right now, we have a array of cards, but that's just because we knew how many total cards we had parsed. But now we're only keeping ones that are minions. Now we could fake it, right? We could go through and, make sure we make the thing big enough, but only take up a part of the array. Or we could go through and count all the minions first, so we knew exactly how many minions we had, and then go through and fill it up with, build the array of the correct size and fill it up with minions. We could do that. Go ahead.
So right now, the card array is like way bigger than the number of things in it, because you only put
Because I only put minions in there. Yep. Okay. So we're going to, let's write our linked list for our cards. So we're going to say, we're going to have a new file, and this guy will be called, well, let's make our node HPP first. And this guy is going to have our, I'm going to steal. Actually, I don't need to steal anything. Where's node? So this is good. Oh, Ninja. Where was I even typing that? Just up here randomly. All right, so we're going to have class node. And a node's going to have a private and a public section. For a node, we're going to keep track of a Hearthstone card, right? That's what our payload is going to be. So we're going to have so we're going to need to import or include, right, in this language, include card HPP. And we'll go ahead and we're going to say we're going to have a, is it called just a card or a Hearthstone card? It's a card, right? Just a card. I'm lost. Where's my note? There it is. Nailed it. All right, so we're going to have a card pointer, and we'll call this guy payload. That's kind of what we've named stuff in our linked lists in the past. So our node is a container which holds our payload, and the payload in this case will be a card. We're also going to have a pointer to the next node, but let's go ahead, since we know we're going to be doing some sorting and stuff, why don't we go ahead and teach our nodes also to know about the previous node? Kind of upgrade our linked list a little bit. We'll do a doubling linked list on this. So, oh, you know what? We'll do that second. We'll do a binary tree of this next, because that will store it in sorted format, right? Oh, awesome. Okay, but we'll do a doubling linked list first. So we're going to say card pointer payload. Then we're going to have a node pointer next node and a node pointer prev node. Okay, so a node needs to know about the guy before him and the guy after him. All right, and constructor for this dude will be called node, and the node is going to take in a payload. And then we're going to go ahead and give ourselves our get payload, get and set next node, get and set previous node. So we'll have a card pointer get payload, node pointer get next node, node pointer get prev node, void set next node, void set prev node. So we'll have getters and setters for our next and previous node. And then we'll have our payload that's going to be a card. So these are the dudes we need to implement over on our node CPP file. So let's create that guy, new file, node.cpp. This guy will include node HPP. Go ahead and add this stuff all over the place. Okay. So our constructor for this guy is going to set the payload equal to whatever payload was passed in, right? So that's going to be, is it this or this in this language, right? This payload is equal to payload. This prev node is equal to nil, which I'm thinking is in, we've been doing null, right?
Null and it's in.
Set standard lib. And then this next node is null. So that's what when we first create an instance of a node, we'll go ahead and fill it up with those things, set the payload, and this guy doesn't point anywhere, right? Get payload. This guy's pretty simple. He's going to return this payload. Get next node, return this next node. Previous node, return prev node. Set next node, and actually set next node needs to take in a parameter, right? So this is going to take a node pointer n. Set previous node will also take in a node pointer n. So I need to update that in my node HPP. These set functions need an input to set it to. Okay, and then this guy's going to go ahead and set this next node equal to n. And this guy will set this prev node equal to n. All right, so that should be our starting point for a node. This is our upgraded node that now knows how to hold Hearthstone cards. Okay, so now we need to go create our linked list. Now we're going to make a simple linked list where this guy is, all we do is we add to fill up the list. We'll go ahead and just add to the end. But we're still going to keep track of previous node and next node for when we do our sorting stuff. Okay. So we're going to create a new file. This guy will be called LinkedList.hpp class linked list. We'll have a private and a public section. Private section, we're going to keep track of the head and the tail. So we're going to keep track of a node pointer head, a node pointer tail. We need to include node HPP. Okay. Who, what? Oh, you want to count? You tell me, you want it?
I could do that.
The answer is yes. I mean, you tell me what you're gonna need to do your homework. Because man, I'm gonna leave this thing at just a dangerous precipice.
I need to write a sort algorithm for a linked list that holds hard values.
Just a dangerous precipice. All right, so we'll keep track of the head, the tail, and the count of this guy. We need our constructor for our linked list. They'll take in no parameters. We want to have like an add end. So void add end. And this guy could take in a card pointer C, let's say. And then maybe a display. Go ahead. Well, not necessarily. I mean, if you're going to add something to the end, you might add a card, have this guy build a node out of that card and then add it. Because I mean, chances are the people who are using this aren't in the business of working with nodes. They're in the business of working with cards. We're just using nodes as our containers. I mean, you could do it the other way, but then you're putting more work on the programmer who's using the linked list. So we'll have an add end and then maybe have a display just to prove we filled it initially. Anything else we need in there? All right, so now we need our linked list CPP. And this guy, oops, this guy is going to include our linked list HPP. And we'll paste this stuff in there. Put that crap in there. I wanted to get this line too. Did you get it? Woot. All right. So when we build an initial linked list, we're going to set count to 0. We're going to set head to null. So we'll have to import standard lib. And then we'll do tail to null. All right, so that'll be our constructor for our linked list, creates an empty linked list. Now we need to go to add end. So now when we add something to the end of our linked list, well, if the list is empty, then we're going to make, and well, any way you cut it, we're going to be creating a node out of this card, right? Okay, so we'll go ahead and create a node pointer n is equal to a new node and build it with our card. We need to import or include node HPP for that dude, right? So now we can create a node. Then we're going to say if. Now we could ask if this list is empty multiple ways, right? We can say is the count 0? We can say is head equal to null? We can say is tail equal to null? We have all sorts of different ways of saying is there nothing in our list. So we can say if this count is equal to 0, that means we have the empty list. Then what do we want to do? We want to have head and tail both point to this dude, right? So we'll say this head is equal to n. This tail is equal to n. All right. And then we're going to, well, any way you cut it, we're going to say count plus. So we'll say this count plus. All right. Otherwise, if we're not dealing with the empty list, then we're putting something onto the end, right? So if we're putting something onto the end, we have a new node that we're putting at the end of our list. So that's going to become the new tail, but we need to make that guy's previous node equal tail, right? and then make tail point to this new guy. So we'll say n set next node to tail. And then we'll set this tail equal to end. Why do I keep saying end? It's a bad variable name. It's just n, not end. All right. So we're adding a new guy to the end. We set his next node to whatever tail currently points to. It's actually not next node, it's previous node. We set the new end's previous node equal to the old end of our list. So our new guy, we're going to set his previous node equal to what used to be tail. Then we're going to update tail to be our new end of the list. Any way you cut it, count goes up by 1. Good.
Should we set the original tail's next node to end before we put tail into node or end tail?
Original tail's next. Yes, we should. Because we're keeping track of both previous and next node. So we're letting the new guy know who his previous node is. We need to let the old guy set next node know who the next guy is to give us the doubly linked list part of it. So new guy knows who comes before him. It's the old tail. The old tail knows who's going to come after him. It's the new guy. And then we update tail to point to the new end of the list. All right, so that gets us a way of going both directions. Any way you cut it, we'll increment count. All right, so that'll be add in. Now we'll be able to test this by going through and did we already teach cards how to display themselves? I think so, right? All right, so now for display, we're going to traverse our entire list. And we know exactly how many times we need to do this, right? We need to do a count number of times. But we also could just keep going until next node is null, as long as there is a next node. But we can say here for display for int I is equal to 0, I is less than this count, I plus plus. So that's the number of things currently in the list. And we're going to go ahead and we're going to have a node pointer cur node and start this off at the beginning of our list. And then we're just going to walk through the list, asking each of our elements to display themselves. So cur node, get payload, which is the card, display. So this is the node. This is the payload that the node holds, which is a card, that we're going to ask that card to display itself. And then we'll set cur node equal to cur node get next node. So this will just run cur node down our list, grabbing each node, extracting the card, telling that card to display itself. All right, so this should be our linked list now, which means back here in driver, we no longer need an array of cards. Instead, do I already have linked list up here? No, I don't. So we will include linked list HPP, which means we actually don't need to include card up here because it's already inside of linked list. And we'll go ahead and create our linked list pointer called, we'll call it the cards. And this is going to be a new linked list nothing in it. And here's us displaying, or here's us building our cards. And now we'll say the cards at end this dude. So we're going to build a new card out of the name, mana cost, attack, and defense. And then we'll go ahead and add that new card to the end of our array of, or our linked list of cards. So now we can get the number of cards we actually collected here by saying the cards. Did I do a get count? My linked list? Killing me. Okay, so we'll go ahead and do an int get count. We'll go ahead and rate this guy. Now we taught our linked list how to return the count element of it. So now we have a get count. So this will give us the actual number of cards that we've stored in our linked list, which should be a subset of 5,217. There's about 1,000, you said? Okay. And then we'll go ahead, we're going to tell our cards to, or our linked list. So the cards display. Tell our linked list to display itself. So instead of using a normal array here, now we have a linked list. Fill our linked list up with only the minions. In the end, display all the minions, proving that it worked, and then write out the number of cards that are in there. Previous definition of class node. This is in node HPP. Oh, and in linked list. This is where you need to do the if not def stuff. But I think we could pull it off here. We don't need node there because we have node inside of linked list HPP. All right, see what that guy looks like. Okay. And there is, so 1,924. So give or take 2,000. All right, so there's our linked list of cards. So now we want to sort these with insertion sort based on, what do we say? Is it health, defense? What was it? Oh, it's called, okay, I got you. So we're doing this on defense from our collection. And we want it to be what? Highest defense first? So ascending, okay. So we'll build this into linked list. So linked list, we're going to go ahead and have a void insertion sort. We'll call this guy on defense. And then we'll write that. So here's our insertion sort on defense. And remember, the way insertion sort works is we start at bucket 1 and we move something towards the beginning as far as we can get it until we've reached our top level. Okay, but we're going to do this through updating our links and stuff like that, so it should be fun. Okay, so we're going to go ahead and we know how many times we're going to have to go through this, right? We're going to say for int I is equal to 1, I is less than this count, I plus plus. And actually, if we want to go off of our, I think the variables we used when we first taught this, I think we probably called it cur start, something like that. Keep going as long as cur start is less than this count, cur start plus plus. All right, and then keep in mind we're also going to have a follower, right? All right, and we're going to go ahead and we're going to actually move nodes around. So we're going to have a node pointer called the follower. And each time through here, we're going to set the follower equal to, we want to get the value that, well, we want to get the node at bucket cur start to give us that position. So it probably would be helpful for us to have a get function that lets us get something from a certain index. But if we want to get the node from that index, and we've talked earlier that maybe we don't want to let external users get nodes, we want them to operate with cards, but we want a node here. We're going to go ahead and make that a private function. So we're going to have a node pointer called get, and this takes in an int index, maybe something like that. But I'm going to make it private, so it's only accessible within this class. And we give it the index, and it's going to give us the node that lives at that index. We'll start with that. That's this guy right here. And for right now, we can just assume they're giving us a legal index. I think that's okay. So we're going to go ahead and say node pointer node to return is equal to this head. For int I is equal to 0, I is less than index, I plus plus, node to return is equal to node to return, get next node. Return node to return. So start at the beginning of the list, zip to where we need to go, updating node to return each time, ultimately return node to return. All right, let's test that real quick. Start at the beginning. This is going to go through. So if I say bucket 5, that'll be buckets. That'll be the 6th element. So we're going to go through this 5 times each time, moving to the next one. Yeah, this works. Okay, we tested it. What's up? fully tested. All right. Oh. Nature. All right. So now we have a convenient way of getting a value. We're also going to write some other helpers as we get into this. We're going to probably want a helper for doing a swap, right? Because that's the scary part of this, right? Doing those, the mechanical swaps, especially now that we have a next node and a previous node. So it's going to be pretty nice if we just solve that one little problem, and then whenever we want to swap two things, we just call swap, and it does the rewiring and all that jazz. So we'll get to that here in a minute. But for right now, we now have the ability to get a value. So we're going to say the follower is going to start off at the same thing as, I made the follower a node, right? Is that okay? Because he's going to follow. But I do probably need to know the index. I want to check him against the guy before him. So we're actually going to make this an int. We're still going to need the get, so we're fine. So we'll say the follower starts off as the same thing as cur start. All right. Now, what we want to do inside here is we want to keep swapping as long as we're not at the beginning. So while the follower is greater than 0, okay, that means that we're at least at bucket 1, which means that we might have, which means that at the very least we do have somebody before me. I don't know if I need to swap with them, but I know there is one. There is somebody before me. So while the follower is greater than 0, and we want to compare the values of the defense, right? So now we're asking, should we swap? So that is this. Where am I? I'm in LinkedList. So this get the follower, get payload, get payload is a card, right? Yeah. There's my get payload. That's funny. It doesn't let you go down. I think it's Visual Studio Code doesn't let you go that far because our card does have that, right? Oh, it doesn't. Why didn't we do that? That's why it doesn't show it to us. So we need to teach our cards how to give us their defense, right? So we can compare defenses. So we're going to have get defense in our card class. And then we'll go ahead and write this guy. Turn the defense. So now back here in our linked list, we should now be able to get defense. There we go. All right. So as long as we're not at bucket 0 and this dude's defense is less than the previous dude's defense, so while both of those things are true, I don't like that formatting. Yeah, that's better. Nailed it. Cherry on top. Dope. Dope. I probably would. I like all food shows. It's more of a fat thing than I think. That's like the worst thing to do is watch food shows when you get in bed at night. That's bad news bears. All right. So as long as I'm not at the beginning and the current dude's defense is less than the previous dude's defense, that means I need to swap 2 positions, right? All right. So let's go ahead and let's write a little function that I can pass in 2 indexes to and say, I want those 2 guys to switch places. Make sense? Let's see. How difficult is it going to be to switch? You know what? We're going to draw a picture for this. I'm going to steal a picture first. Good enough. All right, so now each of these guys though, so our linked list is a little bit more complex now than it used to be, because now they all have previous nodes. So this guy has a previous node and a next node. This guy has a previous node. This guy has a previous node. And then we also have tail. And just for the sake of sanity, I'm going to put my tail variable over here. All right, so that's roughly what our linked list looks like right now, except we actually have cards that live at these positions, right? So this is a card. This is a card. So this will remind us we have to extract that card from here. All right. So the problem that we are trying to solve right now, I'll just get rid of these guys for now. The problem we're trying to solve now is, what if I need these two guys to switch places? Okay. Now, we know in our particular case that we would not be swapping, that if we were here, let's see, it's possible for us to swap. Well, we know we would never be in this position asking about the guy before him. So we know we don't have to worry about that because of the way we're calling our swap. So our worst case scenario is we're right here saying, I want to swap this guy with the guy before me. I want to swap bucket 0 and bucket 1. Okay. And we can even say that we force them to pass in the smaller index and the larger index, just so we make sure they give us, so reduce the if statements we have to ask here in our example. Okay. Actually, you know what? That's not very functional. We should probably just figure that out on our own. All right, so we're going to get our smaller and larger values. So let's say that we want to, in our case here, swap 0 and 1. All right, so let's write the little logic first. It'll take in 2 pieces of information and figure out which one's the smaller one, so we have them in the right order. I think we can do that assumption. Otherwise, it would be an error for us. Yeah, right. So let's go into our linked list here. We're going to make this guy a private function. It's going to be void swap int index 1 with int index 2. And we'll go ahead and write that guy in here. Yep. Oh, that's not where that goes. There. All right, so let's just start with a smaller and larger. We'll make a guess. Int smaller is equal to index 1. Int larger is equal to index 2. If larger is less than smaller, then we'll say smaller is equal to index 2, larger is equal to index 1. All right, so when we come out of here, we're guaranteed that smaller is the smaller index and larger is the larger index. Let's go back to our picture. So I'm going to give myself a couple of these guys. So we have smaller, larger, smaller points to this guy, larger Larger points to this guy. Right now they're just integers, right? So we're gonna actually have to get the pauses there. So this is the smaller card. This is the larger card. So we'll go ahead and get those two variables for us. That'll be back over here. So we're going to have a node pointer. A smaller node. And this will be this get smaller node pointer, larger node equal to this get larger. All right, so like that. So now we actually have these pointers to actual nodes. We want these guys to switch places. So what does it mean to have these guys switch places? I mean, that's where we got to start thinking about the plumbing here, right? All right, so we know that we're going to need smaller nodes, next node, to point to larger nodes, next node. That has to happen, right? Are we allowed to do that right now? Does that break anything? I still have access to smaller node. I still have access to larger node. Can I make this guy point to the same place as this guy and not break anything? Yeah, I think so. All right, so we're going to go ahead and we're going to say smaller node set next node to larger node get next node. Smaller node set next node to larger node get next node. All right, step one, or a reasonable step one. All right, so we've done this. Now, this guy's previous node, right now, can I disconnect this guy's previous node? I need to ask, I need to set it to the same thing as this guy's previous node, which really goes nowhere right now. I didn't actually draw in a previous node for this guy. This guy does have a previous node, which points to null because that was his original prev node. All right, so now I can say larger node set prev node equal to smaller node get prev node. Am I safe to do that? Because I have anchored on to both of these nodes here, right? Okay, so larger node set prev node, smaller node get prev node. Larger node set prev node, smaller node get prev node. All right, back to our picture. All right, so now I need to start connecting these guys up. I already made this guy point to this guy, but now I want this guy's next node here. Am I okay to disconnect this right now? I have something new that's pointing there now, right? So I am okay to disconnect this. So I'm going to set larger's next node to smaller. Larger node set next node to smaller node. Not smaller nodes next node or anything, just smaller node. So I want this guy to no longer point to his old next node. He now points to what will become his new next node, which is this guy right here. All right, what has to happen next? Let's see, we need the smaller node's next node, previous node to point to smaller node, right? So smaller node, get next node, set previous node to smaller node. That's a good one, right? So smaller node, get next node, set prev node to smaller node. So that's this ninja move right here. Smaller node, get next node, which is this guy, set previous node to smaller node. All right, now remember, smaller node's ultimately going to be before this guy. So now we need to set smaller node's prev node equal to larger node, right? Smaller node, set prev node to larger node. Okay, so now we have larger node pointing to previous node, or a larger node pointing to smaller node. We have, and actually if we want to do some relocating for visual purposes, okay, so now it looks like this. So now larger node points to smaller node points back to larger node. Smaller node points to what larger node used to point to, which points back to smaller node. Now in this particular case, since smaller node was at bucket 0, we need to make head point to this guy. If smaller is equal to 0, so it's not smaller node is a node. Smaller is the index of that node. If smaller is equal to 0, then this head now is equal to smaller node. Similarly, if we were down here, if larger was equal to count minus 1, we now need to make tail point to smaller, because these two have swapped. Go ahead. Let's see. If smaller is equal to 0, so smaller would be this guy right here. He used to be head. So smaller is equal to 0, then we need to make head point to larger. What did I write? Oh, thank you. So if smaller is 0, we have a new head, which is going to be larger. Then we can also ask the question, if larger is equal to this count, we're inside LinkedList, so we can say this count. Minus 1, then we can say this tail is equal to smaller node for our swap. So that handles our two extreme situations, right? If we're swapping near the beginning or we're swapping near the end, it makes sure that head and tail point to the right place. But we only update head and tail if we were at one of the extremes. Otherwise, we would be swapping somewhere here in the middle. So in this particular case, since smaller was 0, we now make head point to larger. So now our linked list comes here. So head points here. This guy's previous node points out to oblivion, where this guy used to point. His next node points to the next guy. His previous node points back here. This guy's next node points to this guy, and that guy's previous node points back here. So if we swapped them, they look, it seems like surgery is complete. Okay, go ahead.
If you swap them in the middle, then right now you have, the way you have it right now, like number 1 right now is kind of, it would be pointing backwards, so in the middle, but the one that it's pointing to would be pointing to the middle. You don't need that?
No,
Okay, so,
because we did update this. We set this guy's next node to be back to smaller. That was this line right here. Yeah, this guy used to point here, used to point to nowhere. So we set this guy to point to the same place as this guy pointed to.
yeah,
Then we met this guy point to the new previous guy. So I think this hooks up correctly. All right, so that's what swap does when we swap two positions. So this was our magic here, right? This function, and this is probably our point of failure if we have any issues. So now inside here, if I need to swap, then I'm going to call this swap, passing it 2 indexes. One index, am I going to pass it? I'm going to pass it the follower and the follower minus 1. Those are the 2 things that we need to swap. And then after we swap, the follower follows. So we keep doing that as long as we should swap. As soon as we don't swap, we move on to the next curse start and reset the follower to that place. And then do that whole thing again. So now if I go out to driver, before we display here, if I say the cards, insertion sort on defense, and then display, we should get the largest defense last and the smallest defense first, if we wrote this correctly. Row. Segmentation fault, so that's almost always a memory situation. So let's go back in here. And we could be strongly suspicious that the issue is somewhere in here, right? So let's trace through what we're doing here. This first part seems reasonable enough. We have smaller and we have larger. We're figuring out which one is actually the smaller value and which one's actually the larger value. So I think we could be confident after that code right there that smaller is the smaller index and larger is the larger index. I feel like that code's probably working fine. All right, so now we're into this section here. One thing we probably should legitimately check is to make sure that our get function is working rather than just eyeballing it before we go any farther, right? So let's go back out to driver. And before I call insertion sort here, I'm going to go ahead and I'm going to say the cards dot get cards is my, oh, I made get a internal thing, right? There, we'll just add it to the end of display just as a quick test. My link list. So down here at the end of display, I'm going to go ahead and show like the second to last card or something like that. So I'll go ahead and say this, get this count -2. Get payload display. So the very last card that we should show here is the second to last card from the list, just proving we were able to get something from there, making sure that our problem was not inside of get. All right, so Lyra the Sun Shard. This was last legal one. This was -2. So it looks like get did what it was supposed to do. Seemed like get's working after our exhaustive test. Okay. So that probably gets us to pass these two lines. And we could even test that. Let's just make sure it doesn't die out at that point. So I presume this is not going to crash. Okay, worked fine. So that means, oh, here's my link list. That means we're good up to this point. All right, so just to zero us in on this. A bit of trial and error here. Let's go ahead and find out which of these lines it's dying on. And then we can investigate further. Oh, we know we're okay there. Start with that one. Okay, so it's right off the bat. Smaller nodes, this is an actual node. We're setting his next node to larger node, get next node. Which indicates to me that set next node. I'm guessing this is happening near the front. Let's do a printf of smaller percent D, larger percent D. And then we'll need to import IOStream. Actually, because I'm doing it with printf, this is fine. That'll work. Standard IO.h. So I'm just going to print out smaller and larger. I have a feeling this is happening around near bucket 0. No, it's not. Okay, well, actually, that's maybe a good thing. So this is happening mostly down the line, so we were able to do some swaps. Okay. Well, I mean, I don't think so, because I think we saw, yeah, it's happening somewhere in the middle-ish, because the tail is like 1,900 and some odd, whatever. No. It's probably something that we're doing inside of, remind me later. Go ahead.
Could you draw a picture of what's going on right now with all these swaps that you're
Well, I can, but since we're out of time, this is your homework. Well, I'm going to, and realistically, it's going to be one of these lines where we're not connecting something. So the answer is going to be draw that picture. Something we're not doing something right. So for right now, so homework will be but I put this mistake in on purpose.
Right, of course.
Find and fix swap mistake. And then what I'll do in here, I'll go ahead and push this. Okay, so it's up there. I'll put it up on Blackboard. Okay, I'll see everybody on Thursday. It should actually be a pretty fun one to debug. And actually, I think I know what it is now.
Would you like to share?
No.
I might I articulated it very poorly, but I do think the problem is the thing that I was going to.
I think it's real, but I didn't like it.
I'm gonna have to go back to this second. I think it's funny how short of the description of the comment is on the original. It's like a paragraph and it's like, fix the bug.
Fix the bug.